Today, I'll explain how insertion and deletion work in a B tree. Here's a B tree. Each node contains data, but for better visualization, we'll focus on the structure. First, let's understand the basics. Each node has n keys. This highlighted node here has 3 keys. Additionally, each node always has n keys plus 1 pointers. Our highlighted node has 3 keys and 4 children. The keys in each node dictate where values are stored in each subtree. For example, all keys in this subtree have values less than or equal to the leftmost key, which is 50. Similarly, the keys in this subtree have values greater than the rightmost key, which is 83, and notice it contains 88. Meanwhile, this subtree has values between 50 and 70. Important to note, all leaves are at the same depth. Now let's dive into insertion. For this tree, it equals 2, so the maximum number of keys is 3. Here, t is a parameter you set when creating B trees. Maximum number of keys are evaluated by 2 at t minus 1. Let's start by inserting 41. 41 is less than 45, so we go to the left subtree. Since it's bigger than 38, we go to the right subtree. 41 fits here without exceeding the maximum of 3 keys, so we're good. Next, let's insert 42. However, the highlighted node where 42 should go is full, so we need to split the node. The first step in splitting is to take the middle key, which is 41 in this case, and move it up to the parent. The second step is to add a pointer to the newly split child node. Now we can insert 42. This is how to handle insertion when a node is full. Let's see what happens when both the child node and parent node are full. First, I'll add 60 to make this node full. Now the highlighted node is full and the parent node is also full. So let's try to add 68. When both child and parent are full, we always split the parent first, because if we split the child first, the parent remains full. We take the middle key, 70, and move it up to the parent of this node. Then we repeat the same process for the child node. Now we can insert 68. This is how insertion works when the parent is also full. Now let's move on to deletion. Before we start, there are concepts you need to know: predecessor and successor. Let me explain using key 38. For 38, the predecessor is 30, which is the largest key in the left subtree, and the successor is 40, which is the smallest key in the right subtree. After we delete a key, we replace it with either the predecessor or the successor. Let's try our first deletion, 42. In this case, we can simply delete 42 directly. Next, let's delete 60. For 60, we need to find its successor, which is 62. We remove 62 from its node, then move it up to replace 60. For our next example, let's delete 41. However, if we remove 41 and replace it with its successor or predecessor, the remaining node will not meet the minimum number of keys. In this case, we need to merge 2 nodes, then delete 41. Finally, let's consider deleting 30. After deleting 30, the node becomes empty. In this case, we cannot merge with a child, but the node has a left sibling with more than t-1 keys, so we can borrow a key from the sibling. After deleting 30, we move down 17 from the parent, then move up 10 from the left subtree to the parent. And this is how deletion and insertion work in B trees. To summarize what we've learned today, B trees maintain balance by splitting nodes when they become too full during insertion, and by merging or borrowing from siblings during deletion. The key is always maintaining the minimum and maximum number of keys per node. These operations ensure that B trees remain efficient for searching, inserting, and deleting data. If you found this explanation helpful, please give it a thumbs up and subscribe for more data structure tutorials. Let me know in the comments which data structure you'd like me to cover next. Thank you for watching.